In this video, we'll talk about the fundamental theorem of calculus. In the blue box here, you'll see the fundamental theorem, and I have a little bit of explanation here, and then we'll prove it. So first is to state it. This represents the area under the curve of the little function little f from A to B. And in red, I've explained what that notation means. And it is that the area under the curve of f is equal to this infinite sum. The sum is of f of c sub I times delta x, and I have a little drawing here to explain that. If you think about the rectangular Riemann sum method, we can build a bunch of rectangles inside the curve that approximate the area, and then have infinitely many of them to make them very thin, and thus reduce error like this one has in the drawing. You'll notice that the base of each rectangle is delta x, or some small change in x, and the height is little f of something. I called it c sub I, some ith constant for the ith rectangle. So this integral that we have here is just a short way of writing this infinite sum. And the fundamental theorem says if you want to know what this area is, the area under the f curve from A to B, then you evaluate big F of B minus big F of A, where big F is defined as the antiderivative of little f. Another way of saying that is big F prime is little f. So we're supposing that we can take an antiderivative, and then we plug in the top and the bottom. And if this is true, then we only need the endpoint substituted in, and that should account for all of the rectangles that you can build in here. So first, we'll start with this f of b minus f of a, and we're going to let a equal x naught and b equal x sub n. And what that means is that we have n rectangles. We're going to make n rectangles fit in here. The last input is going to be b, and the first input A. So rather than calling them A and B and having to deal with a lot of letters in between, we'll say that the leftmost point on the interval is x sub 0 and the rightmost input is x sub n. So we're going to work from the right side of the equation to the left. So we'll start with big F of x sub n minus big F of x naught. Now, it doesn't matter how many rectangles we have, so well, it matters to the accuracy, but this limit doesn't change the expression we have above. In other words, this is still the rightmost value, this is still the leftmost value. So now we have a subtraction or a difference of two things, but we eventually want there to be n things that we're adding up. And the way we're going to do that is to create a telescoping sum. And first I'll say that A is x naught, and that's less than x1, less than x2, all the way up to x sub n minus 1 and x sub n. So this just orders all of our inputs. All right, now we can take this sum and make it equal to f of x. Oop, I forgot my limit. Of f of big F of x sub n. And then we're going to subtract and add a lot of things that amount to 0. Okay, so all of these terms are 0, or I can group them to show you that is 0, and those are 0, and those are 0. So we're allowing for lots of zeros. In other words, we're not changing the sum, but we're changing the way it looks. And now I'm going to change the way that you view those differences. Look at these two terms and these two terms. And this guy does have a partner, but it's listed in my dot dot dots. I couldn't write all of them out, obviously. And then these two have a partner. And again, f of x sub 1 has a partner that's included in the dot dot dot, or the ellipsis. So we end up with the sum that we can now write in terms of a sigma. And that sum will be big F of x sub I minus big F of x sub I minus 1. So for example, when I is 1, this will be big F of x sub 1 minus big F of x sub 0, which is this very last group. Or when I is maximal, when I is n, you'll get x sub n and x sub n minus 1. So this sum now is responsible and generates all the terms. Next, we need to take this difference and write it as the sum of something, right? Because our end goal is to have something of this form. So we'll have to do a little bit of a mean value theorem review. So I'll put it in here. The mean value theorem says that if you have some function g and it's continuous and differentiable, then g prime of some spot is equal to the slope. And a little graph of this will show you the slope of that secant line is equal to the tangent slope in at least one place. So g of b minus g of a, that would be a and b here. G of b minus g of a over b minus a gives you the slope of this line, or the slope of the secant line connecting the two end dots. And then this says somewhere in the interval from a to b, there's got to be a c value, and I'm just putting a couple little tick marks where my c value would be. Okay, so I'm going to get rid of the drawing now, and we're just going to manipulate this expression to isolate the difference, g of b minus g of a, and that's going to be equal to b minus a times g prime somewhere. And remember, it's very important that that c value lives between b and a. So here we have the difference of two things, capital F's, right? So the first thing we can do, we're trying to write this, is the difference between the two inputs. Well, what's the difference between x sub I and x sub I minus 1? So x sub I minus x sub I minus 1, the difference between the inputs, we will later call that delta x. And then we have g prime somewhere, or in this case, big F prime somewhere. So big F prime of some value, which I'm going to call c sub I, because each rectangle is different, right? We'll go back to this drawing. Each rectangle is different, so the ith difference has its own special constant that does the job. That's why I've called it c sub I. Well, big F prime is little f. So that's big F prime becomes little f of c sub I. And I'm just reordering the way I'm writing things. And then x sub I minus x sub I minus 1, that is the change in x. So we'll just simply call it delta x. And at this point, we are finished. It might not look like it, but if you go back to the way the integral was defined, an integral is this infinite sum, or adding up the areas of all the rectangles. So I will quickly recap this process. We started with the right side, big F of b minus big F of a. We just sort of properly named what a and b were. And we started with the difference, and we rewrote the difference in a telescoping sum. In other words, think of an accordion, where we can fold the thing back up if we need to, where each of the things that I added and subtracted netted 0. And then we looked at the red bracketed terms to find the sum of n things. This is the sum of n things. It was subtraction. Since we had the difference, we had to appeal to the mean value theorem. in order to get rid of this difference. And a really nice consequence of the mean value theorem is that we get to take the derivative of a function. And because we took the derivative of big F, it landed us back at little f. And then I renamed x sub I minus x sub I minus 1. That's the difference between the two inputs on the rectangle. So we get delta x. And that all of this means that if you want to find the area under the curve, you just integrate or anti-differentiate and evaluate at the two endpoints. And the beauty of the theorem is that all of these calculations of all of these different inputs and the differences among all of those things, it's all calculated for you so long as big F is the proper antiderivative of the function. So the hard part, of course, of using this theorem is coming up with what is the antiderivative. And so the antiderivative will find the area under the curve, and this proves that we can use the antiderivative to find this area every time we see this sign or we're asked anything about areas. And the crux of the proof was solved by utilizing the mean value theorem.